Welcome everybody. So we continue with the second class of control of linear systems. So the topic of this class is the representation and characterization of linear systems, which we have more or less already seen in the last class. The representation and the kind of model we look for a linear system are basically based on differential equation, ordinary differential equations. This course concerns a linear time invariant system in continuous time. So time invariant, we mean that the coefficient of the equations do not change with time. Continuous time, we mean that the signals are take values with t, which is belonging to the dense set, to the real numbers. So in general, the kind of representation we look for in the context of this class is something like this: is a differential equation involving one variable, which is the output, we call it y, but it can be any letter, and another variable which we call input, and is denoted by u. And then a's and b's are just these constant coefficients we were talking about earlier. So you can see basically in this differential equation, a standard ordinary differential equation with the derivative with respect to time, you have derivative of order 0, then 1, 2, etc., up to order n of the variable y, and then you have derivative 0 to m of the variable u, of the input. So the important thing to understand here is that if u is the input, so is the cause of y, which is the effect, it is necessary that the variable n, the order, maximum order of derivative that appears for y, must be greater or equal to m, the maximum order of derivative of u. Why is that so? Well, because if it weren't so, if you had a higher derivative of u other than the derivative of y, basically the causality could not go that way. Basically, y, in order to follow this law, should have to predict the future, to predict what u will do in the future. So the causality, let's say, the fact that y is a consequence of u implies that the order of derivation of y must be greater or equal to the maximum order of derivation of m, and this is what we call the causality. So just keep in mind for now that n is greater or equal to m, and we will come back to this causality issue later on with some example probably. Okay, so this is a differential equation. You are all familiar with this, and for how complicated it could be, you can always find a solution if you have initial conditions. But as I said, the topic of this class, of this course, is not finding the solution, but more studying the properties of all the possible solutions. So one tool we said which we use in this context is the Laplace transform. Why we use Laplace transform? Well, we said it again. Laplace transform is just a change of reference, if you like, for signals, which turns a relationship between signals that are differential in the time domain into algebraic relationship. So let's see an example with this equation over here. Just look at this. So we'll assume zero initial conditions. So for all the variable y and u at time 0, we assume that the value is 0, and also for all the orders of derivative up to n minus 1, so everything is 0. Then we apply the Laplace transform, and here is the trick why the Laplace transform transforms the equation, the differential equation, into an algebraic equation, because every derivative becomes just the multiplication of the signal, the Laplace transform of the signal, time s. So these terms here, a naught time y, becomes just a naught time y of s. Derivative of y with respect to time times a1 become s time big Y of s times a1, etc. If you have a second order derivative, you multiply s squared. If you have n minus 1 derivative, s to the power n minus 1 n derivative s to the power n. So you see, this is what happens on this side, and on the right hand side with u, you just get the derivatives of u becoming u, big U of s times s power 2, etc., s power m. So you see, the Laplace transform has transformed this equation into an algebraic equation. And what has happened here? Nothing special. It is just the same equation, as I said, the same signal in a different reference frame. You can think of it like this, in a different reference frame. So once this is done, remember again, we have assumed 0 initial condition. Otherwise, you would have the initial condition appearing here and then in this equation. But with 0 initial condition, we can just factorize y, factorize u, and basically you get y times a polynomial in S equal u times another polynomial in S. So basically you can write a relationship, a direct relationship between the signal y of S and the signal u of S in these terms. And this is what we call a transfer function. So basically, if you have a signal u entering your system, u of S, you can compute the output y of S in the case of 0 initial condition. I repeat it again, in the case of 0 initial condition, simply by multiplying u of S times h of S. You see it here. So once you have computed the transfer function, what is a transfer function? Is an object, a mathematical object, which is basically a rational function between two polynomials, polynomial in S, polynomial in S. You have an input to your system. Your output is just the transfer function times the Laplace transform of the signal. Pay attention here. H of S is a function of S, but it is not the Laplace transform of a signal. Okay, y of S, u of S are signals. H of S is not a signal. Okay, it's just a factor, if you say, if you wish. That's why we call it transfer function. Okay, so let's have another look of how, another intuition about what happens with differential equation. So you might know that linear ordinary differential equation always have a sinusoidal solution if the input is sinusoidal. So basically, if u is a sine wave, which we can write in a more general way with a complex exponential. If you remember Euler's formula, then you know that the complex exponential yields complex and imaginary part, which are both sinusoidal, cosine and sine. If you are shocked by the use of complex numbers, just think you take only the real part of this one. Doesn't make any difference. So basically what I said is that if u is a complex exponential, which means a sine wave, then y will also be a sine wave. Let's say there exists this solution for a certain initial condition. There exists this solution. Okay, so this is one of the properties of linear systems. It is kind of easy to prove it. You just take this equation over here, replace u, and all the derivatives of u are very easy to compute because the derivative of the exponential is very easy. You just take the same exponential times j omega, and then that's what you get on the u side. You get this one. So basically at the end you can factorize this term again, and you get just a polynomial in j omega, you see. And on the other hand, if you assume that the solution y has this form, so it is again an exponential with the same omega, with the same angular velocity, let's say angular rate, angular frequency, better, with a phase shift we call phi, and an amplitude change we call a. We don't know them yet. We assume that the solution is like this. Let's see if it makes sense. So we just write the derivatives of all these solutions here in these terms over here. So replacing this one, well, the derivatives again are very simple because derivatives of the exponential is just this term times j omega. So basically you get all these terms over here, but this term does not change, and so you get this term, which can be factorized again. And so we are left with this. Is this a solution? Is this solution workable? Yes, it works out if this algebraic equation is satisfied, which basically means that for a given omega, you basically have to fulfill this relation for a and phi such that it is satisfied. So basically, remember that this is y, this is u, right? So y and u, we can factorize and divide one by the other, and basically we get the same expression as before. So we get h of j omega instead of s. So what does it mean? It means that actually this transfer function can be interpreted also as in the time domain, if you wish, as a kind of a gain for one signal to the other, and also in terms of the phase shift that you might have. Okay, so basically y equals u, so they are both sinusoidal, this only if they are sinusoidal. Y equals u times h of j omega. Remember, h of j omega is a complex number, so it has a modulus and a phase, and basically this modulus and the phase are those that you find here, modulus and phase. Okay, and if the system has a steady state, in general we can think that for any initial condition you give a sinusoidal u input, then y will converge to this sinusoidal solution, as you can see in this picture here. So u is the red wave. You input u to a system, a stable system in this case. We'll know better what it means later on, but let's just take it as it is for now. So this system with any initial condition, the output y will converge to a sine wave with the same omega, that's important, with an amplitude which is the same of u times a, amplified by term a, which is the modulus, as I say, of h of j omega, and with a phase shift phi, which is the argument of h of j omega. This is basically written over here. It's written over here. And remember, this h of j omega is just the transfer function which we computed before, replacing s with j omega. So what is the transfer function basically so far? It is a simple way to express an input-output relationship, and it is also a direct map that tells you what happens if you have a sinusoidal input to your output. If you have a sinusoidal input of a certain amplitude at the angular frequency omega, the output y will just be a sinusoidal output with the same omega, amplitude which is amplified by a factor a, which is the modulus of h of j omega, and with a phase shift given by the argument of h of j omega. This is very important to understand because it lets you see the transfer function as a directly useful tool. It's not something abstract, it's a tool which tells you you input your system with a sine wave at 10 Hz, you can immediately compute which will be the amplitude of the output, still at 10 Hz. Now, at this point, it is beneficial to have a small recap on complex numbers, because as you have seen, transfer function, namely transfer function evaluated in j omega, which is what we are mostly interested if we want to use this input-output relation for sine waves. At this point, it is interesting to have a recap of complex numbers, because as you say, we have to compute modulus of a complex number and argument of a complex number. So if you visualize a complex number in the complex plane, on the x-axis we put the real part, sorry, and the imaginary part on the y-axis, and these dots are the complex numbers. Basically, the angle between the positive x and the number is the argument, and the modulus is the distance. So if we have a number, a complex number z, made of x plus jy, sorry, then computing the modulus is basically just Pythagoras theorem, square root of x squared plus y squared, and I'm sure nobody's going to make mistakes on this. Just to recap on another concept is the conjugate of a complex number. You just change the sign of the imaginary part. Now, what is more complicated and brings a lot of mistakes usually is computing the argument. So the argument of a complex number, this angle over here, for example, can be computed by the arctangent of the ratio between the imaginary and the real part. The problem is that this arctangent works only if the real part is positive. Because if the real part is negative, well, you get the wrong result. You can just see, for example, you have a number here and the number here, exactly symmetric with respect to the center. X divided by y is the same. X divided by y is the same. But the angle is not the same. This one is like 60 degrees, and this one is 60 degrees plus something, plus 180. So that's why we have to be very careful when computing the argument of a complex number to check whether the real part is positive or not, as it is written here in this formula. Most calculators or computers have a formula that do this for you, have a function that do this for you, and it's called 8n2 in most cases. Okay, let's see some other interesting fact about complex numbers. So if we have one complex number z, the argument of 1 over z is minus the argument of z. If we have a number z and q, the argument of q times z is the sum of the arguments. Then we have some other interesting things for modulus that is very basic, but please remember these ones. These are very useful, especially in the exercises, because at a certain moment we might need to compute the argument of a transfer function. Imagine you want to compute the phase shift of an input-output relation for a given omega. Then what will happen? Then we will have to take a transfer function like this one, replace s with j omega. J, of course, is complex. All the powers of j will yield either complex or real numbers, and then you will end up with a complex number here, the complex number there. And then you might have to compute the argument of this thing. So basically the argument of the fraction will be the argument of this polynomial minus the argument of this one. Just using this formula. If you have argument of q divided by z, applying these two rules, you basically have argument of q minus argument of z. And then some other interesting things to remember here, some special cases. So the argument of a real positive number is 0. The argument of a real negative is minus is 180 or minus 180. It doesn't matter. All of these you can sum or subtract. 360 doesn't make any difference. And then argument of complex positive imaginary part is 90. And negative is minus 270. Okay, take the time to think it over and digest this information which we need for the follow-up. So let's go back to the interpretation of a transfer function. So we said the transfer function is an input-output relationship under the case of zero initial conditions. So you get a certain input u, your out will be u times h, your output. So let's take a special case in which u is the signal that enters is a Dirac delta. In this case u is 1, so y will be h. So as I said previously, h is not a signal, is a function. But in the case in which u is Dirac delta, then y will be equal to h. So basically you can think that h is the Laplace transform of the impulse response of the system. And this can also be seen in terms of convolution products, but you can read this one if you like, but I don't think it is very important for the sake of this class. So let's continue. There is also another possibility. So far what we've seen so far is one input u and one output y, but this is not always the case. You might have systems that have multiple inputs and multiple outputs. In the previous class we have seen the example of the car has a steering wheel, a gas pedal, brake, etc. So these are a lot of inputs and a lot of potential output variables like speed, position, attitude of the car, etc. etc. So if you have multiple inputs, what happens? The transfer function representation requires you to provide several transfer functions. So let's see an example here. For example, we have two inputs and one output y. So basically, due to the linearity of the system, and this is one of the properties of a linear system, you can compute y as the result of the contribution of u1 and the contribution of u2 as if the other one was 0, and then sum them up together. If you remember, this is exactly what I call the superposition property. You have two inputs. You can assume that the result of the two inputs is just the sum of the two contributions given separately, which means basically that y, the output y, will be the transfer function between y and u1 times u1 plus the transfer function between y and u2 times u2. How do I compute these two transfer functions? Basically, when computing y over u1, just assume that u2 is 0 and vice versa. Now, please pay attention at this expression over here because it is really a deceiving expression. If you just imagine we could simplify u1 and u2, here you get y equal to y, which doesn't make any sense, of course. And this should warn you that actually these two fractions here, they are not to be taken as fractions, but they are basically a symbol to be taken as a whole. Basically it is the symbol of the transfer function. So basically, actually you should be we should be more precise to write it like this. So do not write fractions because they can be deceiving, but just write a transfer function. You see, like h from u1 to y, h from u2 to y, which avoid this confusion. But unfortunately, in the books you will see this kind of expression written here. Just be aware that the meaning is transfer function and not ratio between two singulars, because otherwise this doesn't really make sense at all. Now we move to the next part. Let's have a first quick overview of some simple linear system. So basically we will have an overview of the simple first order and second order system. So what is a first order and second order system? First order system is a system described by a first order differential equation, and the second order system is a system described by a second order differential equation. So basically, because of the properties of polynomials, the transfer functions are just a ratio between polynomials. Every polynomial can be reduced into products of second order terms and first order terms. So basically you can assume that any system is a combination of first and second order systems. So that's why it's interesting to have a look at them. So first order system, in general, if you have a first order differential equation, drawing the transfer function will lead you to this form. You might have an s at the numerator, but the most common situation is this one. So you just have a scalar at the numerator, which we call k, or static gain, and then the denominator is basically a first order polynomial in s which we like to write it this way. So we basically like to have the part multiplying s to the power 0, so without s, equal to 1, and then the number multiplying s, we call it 2. If this is not the case, you might have a function where you have any number here plus any number times s. You can just divide numerator and denominator by any number here, and you're left with 1. So basically you can always normalize this function in order to have a 1 plus something here. And this we like to do it also for second order system. For second order system we have this canonical form. Let's say we have usually a static gain, a scalar at the numerator. At the denominator we have a second degree polynomial in S starting with 1 plus. Then why these two coefficients are expressed in a strange way. So you might have a coefficient, call it A1 here and A2 here. Well, this is equivalent to being expressed with other two coefficients, which we call psi and omega n. Psi is called damping coefficient and omega n natural angular frequency. Why we do this? Because this helps to characterize the system a lot more quickly. So the difficulty is probably you have a polynomial here, you have just numbers here. From these numbers you can just reconstruct the value of psi and omega n. Well, this is very simple. You have a number here, you just know that this number is 1 over omega n squared, so you get omega n, and then you just, what's left here, you can get psi. Okay, so once you have psi and omega n and k, and once you have k and tau for first order, it is very easy to see what happens for a linear system of first and second order when you give some specific standard inputs. So in fact what we are going to look into now is we are going to look into the standard time responses to impulse, to step, and to sine wave. So here h, what is h? Is any transfer function of the kind we've seen before, so either first order or second order. We try different signals at the input and we see what to expect there. Why we do this? Well, it helps us to familiarize with the concept of dynamical system of input-output relation, and also it helps you recognize the first and the second order dynamics, in the sense that if you know what's going into a system and you see what's going out, then you have you can have an educated guess on what is inside. So let's see some definition on what we see when we give when we look at a step response. So we will consider as a standard input the step, the unit step, the gamma function, gamma of t. That function is 0 until 0, then suddenly becomes 1 from time 0 on. So we can have any kind of responses, and we try to identify some specific properties. For example, we have a final value. If the function just converges, it will have a final value, and the y and the output will have a final value, the limit for t going to infinity, y infinity. We might have a peak, a maximum value, and a time of the peak. And then we might have an overshoot, which means what is the amplitude of the peak with respect to the final value described by this formula. Other values, other performance, let's say, that we are interested into is the settling time. So what is the settling time? Assuming that we reach a final value, the settling time, or the 5% settling time, something percent settling time, is the time that the signal takes to enter a plus minus something percent of the final value and stay there forever. So for example, here we have 5% settling time. We take y infinity, we take plus and minus 5%. We draw this tunnel here. So the settling time is the time when this signal enters this tunnel and never goes out anymore. So in this case it is here. So let's see for these step responses what is a typical step response of a first order system. So it can be computed actually. So if the step you remember as the Laplace transform of a step is 1 over s. So if we have a unitary step, it's 1 over s. If we have a u0 times gamma, it will be u0 over s. Initial condition 0. Just multiply this by 1 over s or u over s. Then do the inverse Laplace transform. You get this formula over here. Let's see it drawn. It's basically an exponential which converges asymptotically to a final value y infinity, and y infinity is related to k. Basically, with the zero initial condition, y infinity is equal to u0 times k. Basically, y infinity is u0 times the gain. Then the settling time is depending on the time constant tau, the variable you have at the denominator here, the one multiplying the s when you have a 1 here, remember 1 here. So this is called time constant, in fact, because you can see that approximately the settling time, the 5% settling time is 0.95 times when you enter 0.95 times y infinity is approximately 3 times tau, with a very good approximation. This can be computed. This is not so difficult to do. You can just use this formula here to compute it. If you are interested, try to do this exercise. How to do it? Well, basically when this thing is equal to 95% of this thing, this is the final value, then you find out what is t. Okay, and then you might have another number might be interesting, is what do you have after 1 tau of time? You have 0.63 of y infinity. Then there is a special case which we call the case of the integrator, when basically you have just 1 over s. If you remember in the last class, I've been telling you that if you remember the theorem of Laplace transform, 1 over s is integration operation, so we call 1 over s integrator. So this is one order system, first order system, because we have one polynomial of degree 1 at the denominator. What happens if you have a step at the input? Well, basically the output will be the integral of the step. So the integral of a step, integral of a constant, is a ramp like this. Okay, very well. Let's look at second order models now. You have written in this form or in the other form you've seen previously. And what is the step response for these models? Well, again, you multiply this by u0 over s, as we said before. Then you do the inverse Laplace transform. And the difficult thing here is that the result depends on the solutions of the denominator, basically. So basically it depends on the sign of the discriminant, which depends in turn from the sign of psi, what we call the damping factor. And so according to psi, the sign of psi, which determines the sign of the discriminant, you might have different cases, which we are going to see here. So basically if psi is greater than 1, this corresponds to a positive discriminant, so you have basically two separate roots which are also negative for the polynomial at the denominator, and the step response will look more or less like the first order step response. If psi is between 0 and 1, you will have a step response which might have some oscillation, which correspond to having two complex conjugate roots for the denominator. And then let's look a little bit more in detail what happens exactly. The angular frequency of this oscillation can be computed as a function of omega n and psi with this formula. So there is some oscillation. The oscillation dampened down. There is a peak time that you compute with this formula, peak here, and overshoot also can be computed with this formula as a function of psi. And the static gain again is the same, depends basically on k. So the ratio between y infinity and u, take this one as 0, is basically k. And notice that the oscillations are greater, the amplitude of the oscillation is greater if psi is small. Psi is small. So the small psi tending to 0, what happens? Well, you have a bigger oscillation. So there is a trick also, there is a formula and some methods, empirical methods, well, not really empirical, let's say direct methods to compute the settling time. You can basically use this chart over here. So what is the settling time? Again, is the time you need to enter the plus minus 5% tunnel and stay there forever. You can use this chart here. How do you do it? Well, basically you read here the value of psi on this axis. Pay attention, it is in logarithmic scale. Then you read here your settling time times omega n divided by 2 pi, and if you know omega n, you can compute the settling time. Otherwise, this is this approximated formula. There are some exercises on this that you will do. It is not really difficult. I don't know why some students really have trouble in understanding this. It is you can see it as an empirical engineering solution to compute the settling time. The interesting thing is that this settling time has an apparent minimum here for a specific value of psi, which is 0.69 more or less. So when psi equals 0, that's what I said, you have the oscillation which do not dampen out. Basically the step response of a system which has psi equal to 0, which basically has two imaginary, pure imaginary roots. This continues to oscillate forever. And if psi is smaller than 0, which means you have two roots with positive real part, then the oscillation continue to gain amplitude forever. This is what we typically call an unstable system, but we'll see more in detail what it means later on. Okay. So also here we have a special case, which is the double integrator, so 1 over s squared, where we have a second degree polynomial denominator, it's second order. So you integrate twice, so integrate once the constant, you get a ramp, integrate again the ramp, so the response to a step is a parabola like this, which grows to infinity, of course. And what about the harmonic response now? So for first order system, well, it holds what we see is in general. In general, if you have a sinusoidal input, the output is sinusoidal at the regime if there exists a steady state response. So basically you can compute it again with Laplace transform. But as we said again, if this solution exists, you just need to know that the output will be the sinusoidal with the same angular frequency, just shifted by a certain phase, which is the argument of this one for s equal j omega, and with a certain gain in the amplitude, which is the modulus of this one. Okay, so if you compute the modulus this one for s equal j omega, you get this, right? I replaced s with j omega. Then I compute the modulus. You have 1 plus j omega tau, so this is imaginary, this is real, modulus, right? And argument of this one, so argument is 1, k is scalar and real, so 0 argument, minus argument of this one, which is the arctangent of tau omega divided by 1, so basically this. Okay. So basically you have a sign coming here, you have a sign coming there, amplified by this number, shifted by this phase. Second order model, same story, you just have a more complex computation to do, but the morale of the story is the same. The morale of the story is the same. Just compute this number here for s equal j omega, compute modulus, compute argument. Output is shifted version or amplified version of the input. So in general, the harmonic response is very simple. You can generalize this to any order. Okay, so this is a small example that you might try out. So I give you this transfer function. whatever. Try to compute omega n and psi if you wish. And then what will be the output of an input sinus with omega equal to 1? Well, just replace S with j omega, so j omega equal to 1, so j. Here also replace, compute the modulus, and this will be the shift in the amplitude. In fact, if you use a simulation to do it, this is almost is 5 over 2, so it's 2.5. You will see that for a sinusoidal input of amplitude 1, the output y, the black one, will tend to a sine of amplitude 2.5. Well, this was an exercise. It's done here. It's very simple. I invite you to think it over.